Welcome to the video for section 5.4 of our calculus book, Strategies for Optimization. You'll see on the screen in front of you 6 steps for optimizing type problems. If you're in my class, I've handed you a copy of this. If you're not, you may wish to just screenshot and save this somewhere, print it out, whatever you need to do. If you get stuck, if it's not a really simple problem, these can be good steps to work your way through and help you find a solution. What we're going to do here is we're going to dive straight into some optimization examples. And optimization is a pretty important branch of mathematics. You want to maximize your profit. You want to minimize your cost. You want to maximize your volume, things like that. So we're going to look first at a very straightforward problem where we have two numbers that sum to 20 and we want to maximize the product. So first thing we're going to do is think about the idea of sum to 20. If we make one of our numbers x, then the other one must be 20 minus x in order to have them sum to 20. The product, p of x, will be x times 20 minus x, which is 20x minus x squared. Finding the critical points, we just very quickly take the derivative of p of x and we get 20 minus 2x. And setting the critical point equal to 0, we get that x must equal 10. So the points we will need to test are critical points and endpoints. X equals 0 and x equals 20 are the only possibilities, assuming two positive numbers. And then very quickly checking the second derivative, we get that the second derivative is equal to -2, which is less than 0, which implies that this is in fact a maximum. And we can very easily check that p of 0 is equal to p of 20, which is equal to 0. Therefore, our maximum product occurs at x equals 10. All right, let's do a quick second example, example 2. And we are going to inscribe a box, a rectangle under the curve y equals sine of x, which means that we know that this point P has coordinates x comma sine of x, and an inscribed rectangle will naturally be symmetric. If this is x, this is pi minus x, and therefore this length right here is pi minus 2x, and this height right here is sine of x. We want to maximize the area of this box. Well, the area, a of x, will equal pi minus 2x times sine of x. And we can distribute the sine of x and take the derivative, and what we get is that the derivative is -2 sine of x plus pi cosine of x. I'm missing something in my notes. Oh, -2x sine of x. Nope, sorry. I was right to begin with. Don't know what I did there. We'll just undo inserting that x. I was thinking about the function, not the derivative. This is not, a prime of x equals 0 is not solvable algebraically. But what we can do is we can plug this into our grapher, and we can just tell it to find the zeros of this function. And what we get is that this will be true at approximately 0.710. Doing the same thing that we did in the previous problem, we could take the second derivative, or we could calculate the area at 0, the area at pi, and we discovered that those are 0, and the area at 0.710 is in fact approximately 1.122 square units, and therefore it must be a maximum. And the dimensions of the box, if we are asked for them, 0.710, and we're going to just plug those back into, let me change colors here. We can plug those back into pi minus 2x and into sine of x to get the dimensions of the box. All right, so there's a couple quick examples to introduce you to proportions. I'm going to stop this video now, and we'll continue with more examples in video 2. Thanks for watching. Hope you learned something.